Hello everyone. Today we're going to go over section 3.2, vector representation. Remember when we're doing this, we're going to be solving for a resultant vector. A resultant vector is a single vector that is the sum of two or more other vectors. And remember, a vector is written with an arrow showing the direction that it's going. Such as if we have something that is 5 units, we would put the vector arrow in this direction. Adding it to something with 3 units, going in that same direction, our total addition would be an 8 units in this direction. However, if we would happen to change this and have something a little different for our vector arrows, we can see if this becomes a 3, but our vector arrow is going the opposite direction, our 3 is now negative, giving this a resultant vector of 2. So remember that this is a simple vector orientation that we've done before and that we can see on here. So let's get cracking at what happens if we don't just have simple vectors that are on the same axis, such as we both had 2 vectors just shown in that example on the x-axis. What happens if the vectors are shown in multiple axes, like the x and y? That's when we have to use the Pythagorean theorem a little bit more. We know that in this triangle that's being shown here, we have a hypotenuse that is equal to the value of our units. Well, our A angle is equal to 53.13 units. We know that's a right triangle being 90. So before we even start, we know that that has to equal 180. So we know that our theta or our B angle is going to be equal to 36.87. And we simply solve that because the total of all 3 of those angles, because it is a 90-degree triangle, has to be equal to 180 degrees. And so we now know some information before we even solve on some of this. But let's what happened up here. If there are 2 acute angles, in the right angle above, the ratio is defined. What is the ratio defined? The sine, cosine, and tangent of angle B. So we want to be able to define that. Again, we can refer back to the problem above. We know that sine of angle B is going to be equal to our opposite. So in this case, it's x over hypotenuse, which is r. Our cosine of angle B is equal to our adjacent, which is y, over our hypotenuse, which is r. And then our tangent of angle B is going to be equal to the opposite, which is x, over the adjacent, which is y. So we kind of know that already from geometry and starting in algebra 2 just a little bit more. So we have some of that information already given to us. Ooh, it is moving quite weird. So if we start working on this now, it says use the above definitions to verify the lengths of the 2 legs for the right triangle A. So we know a couple things already. A is going to be equal to our 53.13 degrees. That's our angle. And we know our hypotenuse or R value is equal to 5. We don't know what it is, so we're just going to write units. Could be meters, could be centimeters. We're not really sure at this point. So with this, we are going to solve for those lengths. So the first thing that we're going to need to do is we are going to need to find our y. And so we have to use sine for that. So we know that sine of A, which is 53.13, is equal to our y over r. We don't know what our y value is, but we know our r is 5 units. When we solve for that, we can see that our r is equal to 3.9999, and it's repeating. So we'll go 4 units. To find our x value now, we need our cosine, still of our 53.13, is equal to our x over r. And we know that our r value, our hypotenuse value, is going to be 5. And so when we solve for this, we get 3 units. So if we did the same thing for angle B, knowing the same concepts, we know that our theta, or our angle for B, is equal to 36.87 degrees. That's because we have a right triangle there, and r does not change. Our hypotenuse is still our 5 units. No change in that value. So this time when we find our sine, we have to go our x over r because of the location. And so we know x is equal to what we're looking for, and 5 is our hypotenuse, giving us a value of 3 units. If we look at the problem here, it says our x is still equal to 3 units, and when we use the other angle from above, the x was also equal to 3 units, verifying that they should be the same answer. If they're not the same answer, that's a double check saying, hey, I did something wrong. Now, if I use our cosine, we still want to use our, I forgot our 36.87 degrees here. 36.87 is being used here. It's going to be our y over our hypotenuse, which is equal to y divided by 5 units. Taking the cosine of 36.87, multiplying that by 5, we still get our 3.99, which, if we remember from above, that is the same unit value as what we already had. So we're going to put that equal to 4 units. Again, just kind of a double check that we solved this correctly. Above, it was also 4 units. So we'll have that same value in both spots. So now that we've done that correctly, we have found that we have 3 units and 4 units for our triangle above here. So then that becomes our x value and our y value. And so we can see on here that we have an x value of 3 and a y value of 4. So what if they give us some additional information and ask us to solve for that? Ooh, it's trying to move my values. Interesting. So let's go down to the bottom of the page. And here's an interesting thing. It says here that we have angle C, or vector C, is equal to 10 units at 30 degrees, while vector D is equal to 20 units at 60 degrees. Find the components for vector R if vector C plus vector D is equal to R. So we have a couple pieces of information that we already know. We know that C on the x plus D on the x, because we have both an x and a y, is going to be equal to the value of C, which is 10. Then we want to use cosine because we're looking for x, so we're going to use our cosine. Hint, when we look for x, we typically use cosine. And then we're going to go at 30 degrees. We're going to add that to our D value. Our D value, we're going to start with 20 because that is our unit value here, and go cosine of 60 because that's our degrees for that. So again, we're solving for x. So what do we get for this? So our 10 cosine 30 is 18.66 plus our 20 cosine 60 is giving us 10, giving us the correct answer of 18.7 units. This is on the x axis, not the y, just the x. So we do know that we're going to have a y-axis, so we have to now solve for that. So we solve for y, we typically use sine. So we know c of y plus d of y is equal to, we're going to use sine. We still need to use the units. 10 units is for c. Still have the angle of 30, but so we're using sine plus 20 units for d, sine of 60. When we solve for this, you're going to notice that we have 10 times sine of 30 is equal to 5 units plus 20 times sine of 60 is equal to 17.3 units, giving us our y being 22.3 units. So when we would write our r value, knowing what we have for our r is now our resultant vector. Again, we're writing that arrow above it, showing we have a vector. We know that our x value is 18.7 and our y value is 22.3. So we're just writing that x and y value as we would plot that. So how do we find out what the r is by itself? Because if you notice right here on the very top, when we looked at all of this, we don't have an x. Our c and d values just have one numeric value for the units. It's 10 with a sine of 30. So that's the length of the line. So far, we have just found the plotting points, but that doesn't really tell us the answer. So we use the good old Pythagorean theorem. I know, we're waiting for it, right? So remember that a squared plus b squared equals c squared. Really, that a, b, and c can represent anything. For us, it's c squared plus d squared is equal to r squared. And in order to find that r value, we have to take the square root of our 18.7 squared plus 22.3 squared. And we get our r value. So this is really that r vector that we're looking for, and that is 29.1. That is what we call the magnitude of this, because remember, vectors have both magnitude and direction. So we've now solved for the magnitude. And so remember that magnitude is right here. Remember, for our c value, the magnitude was 10, and for our d value, the magnitude was 20. So now that we found the magnitude, we don't have a vector yet. We just have a magnitude, a value. It's like speed. It doesn't mean anything quite yet. We have to have a direction for it. And in this case, because we're dealing with an angle direction, we need to use our tangent. So in order to find our tangent, we find tangent of theta, theta being angle, is equal to our 22.32 divided by our 18.66. Tangent, we know that we can't solve just for this because there's no angle here. You could also write it as our theta, or angle, is equal to the inverse tangent, because we both know that that's what we're going to have to do to get this. And putting that 22.32 divided by our 18.66. And when we solve for this, we are going to get an angle of 50.1 degrees. And so when we're writing this final value for our r, so we have both a magnitude and a directional value for this, we want to have our r is equal to r vector is equal to, and we want to put our magnitude first, which is 29.09, with a comma giving our direction, 50.1 degrees. This should be written just as it is above, because now we're finding that vector with both a magnitude and a direction, showing the arrows going in the same direction. When adding our vectors, remember that they'll go in the same direction, but when subtracting, sometimes they'll go in the opposite direction of what they're necessarily supposed to go to, because they're going to have a negative value associated with them instead of both being positive values.